So thanks everyone for joining today. So many of you, that's impressive. So this is our, I believe, third meetup, right? We did one virtual. Yep. That's the second physical, in person, should I say. And moving forward, we're going to do, when's the next one? In
June.
So June?
30th of June.
30th of June, and after that, so we have a break in summer, like we don't do what in August, don't do one in August, and then we'll start again after this. So this is DOK London. So it's the little sister of Data on Kubernetes, locally in London. And over time, we hope to have more cities all around the world. It's going to be a lot of fun. So the program for today is going to be focused around, again, I mean, the topic of DOK is to talk about stateful workloads running in Kubernetes, so things around, databases, message queuing. And for today, I wanted to talk about something a bit different, which is more around, the monitoring stack in Kubernetes, but still, the E for EFK, which stands for Elasticsearch, Fluentd, and Kibana, is still stateful. So it makes sense to talk about Elasticsearch. So the program for today, I'm going to be talking on this. I'm going to walk you through a lab just after our, I would say, 20-minute talk. So 10 minutes for Michael introducing Canister. And then I will be introducing the EFK stack and also talking about stateful set, what are the main differences between stateful set versus deployment and stateless application, these kind of things. And then after, we'll have a panel with 3 ladies and pretty famous in the industry, I would say. So we have Cheryl here. That's all the rock star panel. We have Cheryl Hung there. We have Anais. And we have Jennifer, who will be the moderator for the panel as well. And the topic will be mentoring. And can cloud native be done without mentoring? So also interesting. So the lab will probably take about an hour. So we'll probably ideally kick off the panel at 7:30, a bit later maybe, but yeah, hopefully we should stay on track. So essentially, DOK London, as I said, all around stateful workloads running in Kubernetes. We have a monthly meetup. So for people who are going to watch us, if you're not subscribed yet and you are local to London, please do so. The difference between DOK London and the global DOK community is that DOK London, I really want to focus on hands-on labs. Like how can we get hands-on, around stateful sets, stateful workloads, and basically everything around, what you can combine with stateful sets. So things around DevOps, pipelines around stateful sets, everything focused on development of stateful application. Of course, it's community-driven, so you can join the DOK community Slack, which is displayed there. So, Michael, it's now for you to start with your section. So, up to you.
Yeah, nice one. Hopefully the audio's all good. And apologies first up is that I couldn't be there today. I had a bit of an issue here at home that forced me not to come in or not being able to get into London. But hopefully everyone can hear me, and yeah, we'll get on with what we're going to talk about. So as Nic said, talking about like EFK or the EFK stack and the Elasticsearch database as such, or the data service behind it. And the importance of that state or stateful data really is the key message that we're going to focus on today. So at first, I really want to talk about, okay, how do we look to protect that data? How do we look to take native ways and then bring consistency to that? And so I'm from a company called Custom, which is data management from a across all of the different platforms, whether it's Kubernetes, virtualization, physical. And one of the open source projects that we have, and we have been maintaining and contributing to for the last few years, is something called Canister. And it's really focused on an application-centric framework for data management. So think about things like Postgres, things like MongoDB. They all have native ways of being able to query the database system and be able to then like take a tar or a PG dump or some sort of native extract of that data. Now, what Canister does is it's cloud native, so it's deployed within your Kubernetes cluster. We'll get to what that looks like in the lab. And what this will do is go inside of your database or data service. In this case, it will be Elasticsearch, and it will extract that out into an export location, which generally would be something like object storage, and I'll touch on that as well. But really, it's focused on, let's get that application-specific data without causing any downtime or disruption to the data service that we are protecting, in this case, Elasticsearch. But we have blueprints across the board for Postgres, and it's an open source project. Canister.io is a good place to go and see all of those example blueprints. So if we go to the next slide, Nick. So there's three key elements when it comes to Canister and the configuration of that. And yes, you could absolutely go through and you could go and create these cron jobs, and you can go and create scripts to go and do all of this. What Canister does is simplify that methodology. So if we think about the blueprint, this is going to define how we back up, restore, and delete our data. There might be a use case where we do want to delete or mask the data within a data service, especially if we're cloning it back into a test and development type environment. And really, it's going to leverage some of the Canister functions, whether it be kube task or kube exports. But we don't need to get into that too much. But really, a blueprint is there to define what data service and how we're going to protect that data service or restore that data service. If we go to the next slide, Nick. Now, in order for us to trigger that blueprint or leverage that blueprint, we want to be able to run that, or we want to be able to use that blueprint. And this is where an action set. So again, this is just another way of being able to trigger those blueprints to activate and work the way you want them to do. Now we'll have an action set to back up our data. We'll have an action set to restore our data. And any other action sets in terms of, I'm going to leverage this blueprint to do this. We've got one that's specifically aimed at PVCs and not looking after the application at all. So think about if you've got a persistent volume claim that just contains unstructured data, there's no data service linked to it, it's just full of files, and you want to move it from one place to another, migrate it into a storage vendor, as in Ondat storage system, we can absolutely use Canister to enable us to do that. Maybe you're going from native storage PVCs to Ondat. So we could do that as well as part of a blueprint. So if we then go to the next slide, and then a profile is, well, where are we going to send our backups, or where are we going to restore from? So we have a profile, we call them profiles within Canister. And this is literally us saying, I want to use a GCP or a GCS bucket, or I want to use an Azure blob storage. I want to use S3 compliant, whether it's AWS or on-premises S3 locations. So that's kind of the three key areas that we have, and these are cluster resources that we have within our Kubernetes cluster. Canister is deployed via a Helm chart into your Kubernetes cluster. It lives within its own namespace. The blueprints are then deployed out into the Canister or to the data service namespace, and then they all talk to each other via those cluster roles. So if we go to the next one, I'm just going to paint the picture of what this looks before I get into the diagram. So from a Canister CLI point of view, there's two in fact that we use. CanCTL gives us the ability to create those profiles that I just mentioned, as well as the action sets. So from our terminal, and again, you'll see this in the demo lab. And then we also have something called Candu, and Candu really lives inside of the Canister deployment pods that actually trigger, or inside of the blueprints that trigger the push and pull of that data, whether it be for backup or for restore. Now, if we quickly run through some of the visuals of that, the next slide, Nick. So think about, we've got a controller. So Canister's been deployed in our Kubernetes cluster in its own namespace. We have our blueprint that is focused on whatever that database workload is. And let's, for this example, call that Elasticsearch. But again, could be any, like MySQL, Postgres, Mongo, as I mentioned. If we click on, then we create an action set, and that's going to trigger that, trigger the controller to then push the blueprint. Oh, this is what I want to do with that. And we use a canister function, depending on what the action set tells us to do. And then that starts to send it out. And I'll see if me and Nick can time this, sends it out to our object storage, either as a cloud snapshot leveraging CSI or leveraging just basically a lift and shift of that data. And then from a restore point of view, just rewind exactly what we've done. So that's a very quick overview of Canister, and I'm going to let Nick go through the EFK stack. I think I've already mentioned it as well. The Canister.io is a good place to go and get started, as well as what we're going to actually get hands-on with later on will give us the ability to see a little bit more about Canister and how it works and what the reasons are that we're using it for. So all the information's on there. It's pretty simple to deploy. We're going to do that in the lab, all of that good stuff. So yeah, over to you, Nick.
Thank you, Michael. It was great. Okay, so I'm going to try to make it also quick so we can go through the lab. So just so you can prepare yourself, for people who wants to do the lab, you can get your laptop, and then the Wi-Fi password and SSID is written there. Yeah, it's a code node, that's the SSID, and the password is enter space, capital E, capital S. All right. Okay, so today we're going to focus on the EFK stack, so composed of three main tools. So all of them are open source. So FluentD is, I think, graduated from the CNCF. So it's log collector and shipper. It can collect from different sources and forward it to monitoring engines. Can be, in our case, Elasticsearch, can be also other solution or cloud-based solution. It is deployed as a daemon set in Kubernetes, which means that it's going to sit on every single node inside from your cluster. And really, its job is to streamline all the logs into expected formats. So it's really about getting the logs collected and shipped to a centralized database. In our case, the database is Elasticsearch, which is a real-time distributed and scalable search engine. Can be used to index and search through volumes of log data. So it's really fundamentally a NoSQL database that can store JSON documents. So there's two terms to get. The first one is the equivalent in the relational world would be a database. The equivalent is an index inside Elasticsearch, and a row, for example, inside a relational database in Elasticsearch, it's called a document, right? So the idea is also to leverage what we call inverted indices, which means that, for example, if you have a lot of logs that, let's say, with the word Kubernetes, for the specific word Kubernetes that is recorded inside Elasticsearch, it will be mapped to all the documents that have effectively the word Kubernetes inside it. So it's very fast and very scalable. So it makes sense to use it for, if you want to scale your logs and also very efficiently search for particular logs. And then we have Kibana, which is a tightly integrated with Elasticsearch. It's a tool to visualize, query, and filters data from Elasticsearch. We have the three main components. Elasticsearch, which is the central database. FluentD, whose job is really to collect all the logs. It's logs from pods, but also from any, I would say, internal service like kubeproxy or kubelet. All that can be also sent to, collected by FluentD and sent to Elasticsearch. Okay, so in terms of the architecture, it's pretty simple. We have FluentD that is, again, sitting on every single node managed by a daemon set. Collect the log, send it to Elasticsearch, Kibana as the front end, and we have, of course, a Kubernetes PVC for the Elasticsearch node. So typically, you deploy Elasticsearch either through Helm or through, you can also deploy directly with manifests. But the most important thing here is that it's going to be a stateful set. And I'm going to now move into stateful sets and volumes in terms of, I don't know if every one of you is familiar, so we're just setting the stage here. What are Kubernetes volumes and what is specific to stateful sets? So Kubernetes volumes at the origin, I mean, you can have a lot of different volumes mounted within Kubernetes, not necessarily only data volumes. You can mount things like config map or secrets or downward API, which is basically feeding information, contextual information from Kubernetes itself back to your application, which may be very useful. Instead of hard coding things in Kubernetes, the pattern to do it in Kubernetes is not to hard code anything. If you have environment variables or anything that can be retrieved from the environment itself, then you should use the platform. We have ephemeral volumes, host path, and MTDR, which is more around local data. And of course, probably the most known usage of volume within Kubernetes, which is persistent volume claim. And originally, they were built-in tree within Kubernetes, meaning that all the driver were in the core code of Kubernetes, but it's been moved away from that principle to give more flexibility for vendors and other providers to build their own modules and their own plugins. So now it's called the interface that is sitting between Kubernetes and the storage part of the world is called a CSI, so Container Storage Interface. And it's been there for a couple of years, I think like about 4 years. If you want a quick trick, if you want to see all the supported volumes, I mean, some of them are deprecated. There is kubectl explain, which is your best friend when it comes to finding documentation and different fields and options. And then you can just use pod spec volumes, for example, and -- recursive if you want to see the whole list and all the options at once. So in terms of the Csi driver, to date, the main mechanism to interact with your storage, as I said, it was defined in 2018. Previously, it was in tree, so with flex volume. But now, the main focus of the Csi is to enable external provider and contributors to interact with Kubernetes and align with the innovation that Kubernetes is bringing. So especially in terms of doing backups, snapshotting, cloning, resizing, as we see more and more interest for hosting stateful application within Kubernetes, it makes sense to bring the same capabilities that you could expect from any enterprise solution that has been living for the last 20 years on premises. And the idea is to really bring all those components within Kubernetes to keep it cloud native. So we have dynamic provisioning, deprovisioning of a volume, attaching, detaching a volume from a node, and all that are functions that are basically called from the CSI, and it's up to the vendor to implement them. But everything is transparent for the user. It's just a very easy and pluggable system. So of course, mounting and unmounting volume from a node, creating, deleting snapshots, and also provisioning new volume from a snapshot, which may be useful, especially if you're developing stateful application and you want to shift left your data. So by shifting left, I mean bringing more tools for developer, very early in the development cycle, so that you limit the number of bugs and get a similar, data set that you have in production, and very easily bring it up to the developer very early in the development lifecycle. So in terms of the primitive, there are essentially two things that are managed for storage. First, we have the persistent volumes. You typically don't directly work with persistent volume, but they represent effectively the storage that is sitting, the volumes that are sitting behind the abstraction layer. So typically here, you can have persistent volume. You define the access mode. You define the behavior when the pod get deleted, for example. But all of that, normally, you don't really touch the persistent volume. With dynamic provisioning, the idea is for the persistent volume to be provisioned dynamically. Before that, people had to, and admins had to, first create the persistent volume, and then what was linking the persistent volume to pods was the persistent volume claim. So it's very common now for dynamic environment like cloud or even on premises for the CSI to dynamically create the persistent volume based on the PVC. So for example, here we have a persistent volume claim that is just derived from a storage class. And the dynamic provisioning nature of the CSI will just provision the underlying PV when the pod gets bound or attached to the PVC. So in the order, we attach a PVC to the pod, and then the PVC and the CSI will take a look at the PVC. Okay, I need 5 gig of storage from that storage class, which map in turn to that particular storage solution, maybe a storage array, maybe EBS in AWS or any of the persistent disk in Google, this type of things, and they will get created automatically. That's the idea. But now, what is the main difference between, let's say, traditional workloads in Kubernetes, like stateless containers, as opposed to I would say stateful applications? So first, I would say, or I would argue that there is no per se, stateless application. You always find a stateful component within an application, right? So you may have your front end that is stateless, but at some point, if you're building a web application, you need to store your, I don't know, maybe your customer data, or maybe if you're logging anything, it needs also to be stored, right? So even if we build microservices, you always have to have, some sort of databases. And although at the beginning, a lot of people were arguing for or advocating for stateless container running in Docker and later in Kubernetes, now we see more and more, I would say, reason to host stateful application like databases into Kubernetes. So cost is the first reason, flexibility, second one, and also as you migrate workloads into Kubernetes, you can also take advantage of all the Kubernetes, high availability benefits, right? So, but essentially the main difference between a deployment or a stateless application and stateful workloads is the construct that you're going to use. So stateless, you will use a Kubernetes deployment. Stateful, typically you use a stateful set that was, they were originally called, I think, pet sets. But yeah, now the name is really stateful set. So if you look at the diagram, you will see that typically a pod, when you create a deployment, you will have a controller that will manage, so the replica set controller that will manage the number of pods that you want to set into your deployment. And once you attach the deployment into a PVC, all the pods within that deployment will share the same persistent volume claim. So what that means is either two things. Either you can have, let's say if you have 2 pods on the same host, only the first one that is going to claim the PVC will be able to write data to disk, not the other ones. So typically you don't want a direct attach, block storage for that. The only way to make multiple pods write to the same PVC is basically to use a shared file system. Right? So typically that means that you need some NFS share or read-write many here in Kubernetes. So the different access modes are written there. So we have read-write once, read-write many, read-only was X for, read-write X stands for multiple times, I believe, and read-write once for pod, right? When you allocate, only the first pod can claim the PVC, and no one will never be able to touch it. So, but the problem is if you're building a database or something that needs some performance, then NFS is not really suitable, right? So basically that means if you need to deploy a database or something that individually, make up a cluster. For example, if you're building, so Elasticsearch, right? That's a good example. It's building a cluster of nodes, and those nodes need to have dedicated storage space. So of course, a deployment in Kubernetes won't work for that. So this is where you want to use stateful sets. So with a stateful set, within that particular construct, you can use something that is called a volume claim template. And that particular volume claim template will allow every pod part of the stateful set to consume its own storage space and get its own storage associated. That's one part. And then the second part of the stateful set is that it's going to maintain a stable identity for every pod of that stateful set. So what that means is, as opposed to a deployment where if a pod dies, then another pod will take its place with a new name, a new network identity. With stateful set, it doesn't happen this way. Every pod will have a stable name and will keep the name. So if you have, let's say, Elasticsearch-0, and of course the pod, they will start from 0 and then increase the ordinal number, so it's super predictable, right? So we will have -0 that will have its own PVC, then -1 will have its own PVC, and if -1 or -0 fails, then the next pod that's going to take its place is going to have exactly the same name, will be attached to the same PVC, the same data. So if you are building a cluster, it makes the cluster, it's a lot easier to sustain any failure, right? Because you're sure that the data will be there, and the cluster won't be impacted by any failure. That's the idea of the stateful set. On top of this, we have an extra component that needs to be there. It's called a headless service. So as opposed to a traditional service, a Kubernetes service, typically, if you want to expose a service internally to the cluster, you would use what we call a cluster IP, which very easily is just a load balancer that will point to one of the pods part of the deployment. A headless service will allow, instead of having a load balancer, it will just return A records for every pod that is set as an endpoint for that particular service. So in the case of Elasticsearch, if you create a headless service and you do a DNS request to that FQDN that mapped to this headless service, you will see a list. If there are 3 nodes, you will see a list of 3 IP address, right? So the IP address, if the pod dies, the IP address will change, but the name won't change. That's what makes a stateful set stable. Okay, so, and now the question comes, how do you provide storage for those stateful set? There's typically, multiple options. You can use, if you're on premises, you could use a storage array and map it to your Kubernetes nodes. You could use NFS, shared file system if you wish so, but or you can use a software-defined, solution like a vSphere, vSAN. You can use this type of things, but I would say, like, for the last couple of years, new type of solution have appeared, which is container attached storage. So a good example of this is Rook plus Ceph, and also Ondat, of course, that is on the next slide. So what it allows you to do is to leverage the local storage of the nodes and turn them into a centralized storage that can be consumed by every node and implement extra capabilities that are not present in Kubernetes by default. So that includes things like replication, right? By default, Kubernetes doesn't provide any replication. So it can be synchronous, asynchronous replication. Things like encryption is not there by default for your storage, right? You may rely on maybe your cloud provider to do the encryption, but how can you guarantee that you're going to have end-to-end encryption? It's not really possible in AWS or in any cloud provider. So that's a good way to keep your storage performant, increase the capabilities of Kubernetes, because, for example, if you have a node that has a PVC attached to a pod, if that node fails, well, you're in trouble because the pod won't be able to restart on another node because the other nodes don't have access to that storage, right? So, but if you replicate the storage from node 1 to node 2, if node 1 fails, then suddenly the pod can be restarted on node 2 because the storage is there, right? So it's a lot more efficient, and it just increases, Kubernetes availability and resiliency in general. So as an example with Ondat, you have multiple way of presenting the distributed storage. So here, this is the centralized storage where you're going to dedicate a couple of nodes to to present the storage capacity to your application, and you can dedicate other nodes to compute. Or you can go for the full, I would say, the full-blown, storage, distributed storage, where you have every node that is participating into storage capacity. And you can control how many replica you want, and regardless of the type of drives you attach to the node, we can leverage this storage and then present it to the pods. Or some more people are joining. Hello, please take a seat. That's okay, because we didn't start the lab yet, so it's just on time. It's just the fluff at the moment, just the theory. So yeah, the idea here is to enhance Kubernetes native capabilities so that you can satisfy the requirement for stateful application, because stateful application are critical application for enterprise. So this is your business application, and most of the time you cannot really afford to lose data or to lose just, in terms of RPO, RTO, it has to be close to zero. But now there's also the question I've got often asked is, okay, but we can also have replication at the application layer, which is true. So why do you need replication at the block layer? Well, there's a couple of things. So first, of course, if you lose a node and if you lose data at some point, or if you write something that is wrong to your disk, and if the application is just replicating this, you're in trouble, right? So this is why you need things like snapshot, backup, to guarantee consistency. Another reason may be that as much as possible, you want any failure for the application to be transparent. Because sometimes, cluster recovery doesn't work perfectly, right? You may have to manually recover nodes, things like that. If you guarantee that in case of a node failure, or just like in case of storage failure, you can have a replica that can take over, within seconds, transparently for the application, even though the application itself has some sort of redundancy, then you're safe, right? That was the same problem 10 years ago with things like vSphere or vSAN versus a storage, or if you run a database in vSphere, do you replicate your storage, or just do you replicate at the application layer? And most of the time, the answer is you want the belt, and you want also, you want everything. What's the name for the? Suspenders, exactly. You want the suspenders plus the belt, right? So this is why you want to translate this sort of, paradigms into Kubernetes as well. Okay, so now we can start the lab. So this is the link for the lab. This is play.instruct.com/ondat. So I don't know who wants to do the lab. Guys, you want to do the labs? Or I will do it. So there's two ways to do it. Like either you can follow along and just look at what I do, or you can follow this link as well. But before that, I've got a little Kahoot. So we had two choices: either do it before the session or like just now. But because I've spoken about some notion and paradigms that are asked during the for the quiz, then it's easier for you to get it now. Okay, so where is it? It is there. So this is this one. So if I do play, start. And we have some prize. So for the winner, we have a nice North Face Ondat branded bag as well. Okay, we're going to start classic mode. So you can join from your phone if you want. So you can just go to www.kahoot.it and enter the pin number there. So I'm just going to wait for people to join. Oh yeah, for the Wi-Fi, it's code node, the SSID, and the password is enter space capital E, capital S. Yes, I just need some water. So I'm just going to take some water. So I'll give it a few more seconds. You guys join already? All good? Okay, I guess we can start. So for every question, I put it on 10 seconds, but it's just the countdown starts at the end of the question. So read the question. I think for the question, there's also 5-10 seconds, and then you will have 10 seconds. There's 5 questions. All right? Ready? Okay. Ta-da. So what kind of Kubernetes service is required for stateful pod name resolution? 10 seconds. Node port, headless service, cluster IP, load balancer. Okay. So yeah, pretty good. 2, yeah. Next. So great squid. Well done. Prod crab as well. That's funny names. Which data operation is not supported by Kubernetes by default? Cloning, snapshot, resizing, or replication? Okay. Oh, resize? Okay. So 0, okay. Next one. Canister leverages custom resources to perform data operation. Which resource is not a Canister resource? Profile, blueprint, dataset, action set. Bit of a mix there. So answer was dataset. Okay. So who is winning? Proud Crab's taking the lead. True or false? In Kubernetes, container logs persist after pods are deleted. Okay, that was false. Next one. So who is there? Oh, Prod Crab still first. Oh, that's funny stuff. Kubernetes generic ephemeral volumes can be local or network or attached via the network. True or false? Local or attached via the network. True. Generic ephemeral volumes. This one is tough. Yeah, that's true. Okay. So who is the winner? Third is, where is it? Great Squid is number 2. But now how can I map? Proud Crab. So who is Proud Crab? Now anyone can claim it. Who is Proud Crab? We have the bag. Who is Proud Crab?
It's me, Nick. So you'll have
Oh no! Yeah, that doesn't count. So second, no, you cannot win this one. So who is Great Squid?
I'm Great Squid.
Well, that's you. That's fine. So you won the bag, Cheryl. You had one. So you already have one? So who is, yeah, the third one, champion here. You're third, so you will have it, because yeah, Cheryl and Michael doesn't really count. You cheater, Michael. Okay. So that was fun. So now, more seriously, we can start the lab. So again, should I do something? Record? No, everything is recorded. No, that's fine. I can just start it. So play.instruct.com/ondat. That's if you go there. Oh, by the way, if you want to do it after, the lab is going to stay just forever, right? So if you go play.instruct.com/ondat, you have every meetup will have its own lab. So we have the first one we did was about Vault integration with our open source project Trousseau that allows you to map multiple KMS to Kubernetes. So very fun one. Last one, that was the first one. Second one, we did a mix of policy as code with GitOps. So that was Weave plus Kibana. Again, with pipeline around stateful sets, stateful application, databases, all of that, but with policy as code and also GitOps. It was a fun one as well. And today, the one we're going to be doing is, where is it? Okay, this one. Protect your Efk stack with Ondat and Canister. So I'm going to do it, and you can follow along. Just look at the screen, or you can try it yourself as well. So I'm just going to go read it, I guess, at some point. So in this track, what we're going to do is deploy Efk monitoring stack on Kubernetes. Maybe can everyone see clearly, or it's fine? Maybe I can put it a bit more. Yeah, like that. So where is the top of? So it's essentially divided into 3 parts. So in the first one, we're going to deploy Ondat. So the Ondat will be the, I would say, the solution to provide your distributed storage in Kubernetes. On top of that, we're going to enable replication and also because we want to talk about disaster recovery as well as backup. So we're going to enable a feature that is called topology-aware placement that allows you to guarantee that your replicated volume are distributed and spread across multiple availability zones, so that in case of full AZ failure, whether it's on Google, Amazon, or even arbitrary, labels on premises. So you can say this is rack 1, rack 2, rack 3, for example. We want to make sure that the replicas are, I would say, evenly distributed across all the zones that you have set. So we're going to enable this as well. And then deploy EFK and then use Canister to back up and also restore data in Elasticsearch when a failure occurs, right? So we're going to be using so Canister is leveraging the operator patterns, so a lot of custom resources, which means that we're going to play not too much with YAML, right? I don't know for you, but I have a strong love-hate relation with YAML. But as Michael mentioned earlier, there are command lines that help you build those YAML manifests, so not too much YAML. Okay, so let's start the track. So normally it should be, fast. All right, so maybe a bit smaller, like this. So in the first track, or the first challenge, we're going to be installing Ondat, enable topology-aware placement, and also install Canister. So to install Ondat, the first thing, there's multiple ways to do it. If you want to install Ondat via your GitOps pipeline or in a declarative fashion, we have a Helm chart, and we have also the command line, the kubectl plugin that will allow you to generate the manifest, and then you can include those manifests into a Git repo and then deploy with GitOps, for example. Or if you want to do it in an imperative fashion, you can just first run the the pre-flight check. So StorageOS or on that pre-flight check that will tell you, is your cluster ready to get Ondat installed. So typically we check, kernel modules, we check for memory, we check for CPUs, all those kind of things. And we can just trigger a warning and things like that. And if everything is fine, then you should be able to install Ondat directly on your cluster. So the lab is using K3s, but I would recommend to use a proper solution, enterprise solution, if you want to deploy in production, of course. So here I've got sufficient CPU memory. Then here it's complaining because I don't have NVMe storage, but it's not the end, right? It's NVMe anyway. We won't talk about this today, but a good way to leverage NVMe and Ondat in the cloud is just to use your instance store, for example, or your ephemeral storage attached to your cloud instances. So typically, as soon as you shut down your instance, the storage will get deleted, but because you have Ondat or another storage replication solution that will replicate the storage on other nodes, it's not too important. So you can make the most of your local storage if they are NVMEs, so that you can save on cost because it's a lot cheaper than EBS and it's also more performant. So it's really a win-win. So once you get this, you can quit, and then I'm just going to use the kubectl plugin. So here, kubectl storage OS install, and then we need a etcd cluster to store the Ondat metadata about every single block. There's two solutions today. If you run in production, we recommend to have a dedicated external etcd cluster. But currently, we are still testing our engineering team is still testing and validating that you can just include etcd in your local Kubernetes cluster and still run production-grade workloads. So today is only for testing, but soon it will be also for production, because you want, let's face it, it's a lot easier to get everything into your Kubernetes cluster. And maybe you don't want to have to maintain a couple of other instances running etcd as an external system. So the install should take a couple of minutes. So we create different elements there, but all the common point of all the CAS, so the container attached storage solution, they are based on microservices. So themselves, they run inside Kubernetes. So if you want, the way I like to compare, Ondat to other storage solution, if you remember VMware vSAN, we used to call it hyper-converged for virtualization. Well, container attached storage is exactly the same thing, is hyper-converged storage, or I would say, so converging compute storage on the same hardware, on the same devices, right? So it's exactly the same thing. So all the components run themselves as Kubernetes objects. So we have daemon sets, we have the control plane that is there as a deployment, and we have also another set. We have secrets to encrypt all your volumes. So every volumes will have a secret attached to it for the key, these type of things. So the solution is truly Kubernetes. So once it's deployed, just want to check that you get the, I should maybe put this there. You want to have a ready state for all your, the pod for the daemon sets. So there is effectively an agent, an Ondat agent located on every node. So until we have 3, so we do have 3 now. And if I look at all the pods that are present there, you see here we have a dedicated namespace for the etcd cluster. So we have 3 nodes there. We have then another namespace that is also holding all the control plane, right? And also the daemon set, which is the data plane. We still have a couple of container creating there. Yeah, but now everything is running, that's fine. So the next step now is to create a new storage class and to create labels for the nodes. So the idea, remember, is to be multi-AZ, to provide high availability for multiple AZ or availability zone. So for this, we're going to be using arbitrary label. So in that particular case, the name of the label I choose to use is custom region. So the custom region field will hold the topology domain area, right? So that every node with the same label value will be participating or will be held in the same availability zone, right? By default, if you don't use any, I would say, custom or manually set label, we will use the node topology key, which means that if you're using AWS or GCP or GKE in that particular case, it's automatically populated using the region or the zone you're using, right? So you don't have to do anything. But here, because I'm using K3S, in the same region, I still wanted to emulate different zone there. So the nodes are labeled. So now I need to create a storage class. So the storage class is essentially the Kubernetes object that will store all your storage configuration, all the underlying storage configuration for Ondat. So typically for other CAS-based solution is exactly the same thing. You want to encapsulate your features and your requirement within native Kubernetes object so that developers, they don't have to learn something or to use an extra software or to use another language. And as everything in Kubernetes, everything is based on YAML and on label. So at the top level, you create a storage class, and when you create a PVC that is consuming that storage class, the volumes will inherit and will set all the parameters from that storage class. So all the volumes that are attached or bound to that storage class will all share the same features, right? And if you want another set of features, then you will create another storage class and attach PVC to that particular class. So here it's very easy. We want 2 replicas for every volume. So that's basically 1 primary volumes and 2 replicas. We want topology aware enable. And then the topology key I'm going to be using, the key is custom region, and the value, well, it's an arbitrary value I want to set to classify my nodes. And then you can also change the failure mode. The failure mode just determines, how many. If you don't have enough replica, what do you do? Do you stop? Do you put the application in read-only mode, or do you continue to work? This soft means that I want to continue to work. The file system type, so you can have XFS if you're using, I don't know, Mongo or any database that recommends XFS as the file system. By default, you will have X4. Right? And there's other things like encryption. All of that is based on labels. So very easy to use. Is completely Kubernetes native. So now you want to create that particular storage class. So you just copy that. So just checking that I don't have any. So storage class, I just have the storage OS, which is the default one that has been installed as I've deployed the Ondat solution. And I've got local path, which is just provided by K3S by default. So now I'm going to create that particular storage class. And yeah, it's there. And it has all the feature enabled that I've mentioned before. So the next step now is to, we have all what we need for your stateful application. So now what we're going to do next when we install Elasticsearch is to use the storage class, that particular storage class, to attach the PVC of Elasticsearch so that we can have all this replication. So Canister, which is our solution for backup, again, is based on the operator pattern, which means that it's going to be using custom resources to do some automation. So we have 3 main custom resources that we're going to be using. We have, and correct me, Michael, if I'm wrong or if you want to complete, we have the blueprint. So the blueprint will define what we want to do for a particular application, how we want to back it up, how we want to export the data, something that is specific to the application. So in our case, we're going to be leveraging the Elasticsearch Blueprint. And within that blueprint, then you define, you reference action sets, which is another custom resource. And action set can be restore, can be backup. And we'll encapsulate under the form of container running in the system. Let's say, if we were 10 years ago and I would use VMware, I would need to quiz the file system, I would need to leverage VMware tools and to make the application consistent, right? But here we are in Kubernetes, so instead of using VMware tools, I'm just using containers, right? Because you can just run any command, any task, you can run it as container in Kubernetes. This is exactly what the action set will do. It will do all the heavy lifting to realize things like backup, restore, snapshot, etc., etc. And then we have the third one, which is the profile. So the profile will define where you want to store your backup. In our case, because Instruct is running in Google Cloud, every attendee who run the lab will also have access to a Google Cloud storage. So we're going to see later that we're going to back up the Elasticsearch data into your local, part of the same project, into your Google Cloud storage volumes. Easiest way to do pretty much everything in Kubernetes for today will be to use Helm where we can. So to install Canister, we just add the Helm repo there and install, there. So here, again, Helm install into a particular, we're going to install, so this is going to install the Canister controller, right? So why the controller? Because again, this is aligned with the operator pattern. So you're going to have the controller that is going to monitor the creation of all the custom resources, like Blueprint, Profile, etc., that are added to Kubernetes. As soon as those resources are going to be created, then the controller is going to do some automation and create all the container to do the backup, etc., etc. Right? So it's really nothing but an operator. So okay, it's installed. Just to make sure that the controller is now running here, so you can see it's running. Okay, so that was the first part. Once it's done, just click check to move to the next one. Okay, correct. It was not too difficult. Okay, so in the second challenge, what we're going to do is deploy the EFK stack with Helm, except Kibana. So Kibana Kibana is also, I think FluentD is just a daemon set. Manifest is not part of Helm. Okay, so use Helm to deploy and configure Elasticsearch. Then we're going to deploy the FluentD daemon sets. Use Helm to deploy and configure Kibana, and then we're going to test that EFK is working. So again, we have the architecture of EFK. So FluentD daemon set running on every node, collecting and shipping the logs to Elasticsearch, and we have and then Elasticsearch store everything in the data into a PVC backed by Ondat, and then we have Kibana as the front end for visualization. Okay, so now install Elasticsearch. We're going to be using Helm. So again, we're going to add the Helm repo. Then we're going to check also if hopefully everyone is familiar with Helm. But the first thing to do, by default, if I don't change anything, it's just going to use the standard storage class. And actually, what I want to check is that what kind of values you can change directly in the chart. So here, I just want to check if the volume claim template can be modified. So you can see this is the default settings. There's no storage class associated, so it will be bound to the default one, the standard. The default storage class. And I've got 30 gig, which is a bit high. So what we're going to do is create a couple of new settings. So you can see here we want 5 gig instead of 30. and we want the storage class name on that tab that I've created before. So by influencing the volume claim template, it will have a consequence on all the pods that are going to be deployed as part of the Elasticsearch stateful sets. So that means that every pod part of the Elasticsearch cluster will use that storage class, and then every volume will be replicated across multiple availability zones. We'll be using everything that we have configured for the storage class. And a few things there as well, because the Kubernetes cluster is quite small, I want to decrease the resources, the compute resources a little bit. So now you can install the chart just by specifying the values.yaml, and then it's going to be deployed, and Helm is going to do its job, and you can monitor what's happening. There, it's going to take some time, probably a couple of seconds or 2 minutes, something like that. I don't know, Michael, do you have anything to say, to comment, or to add on what I said?
Yeah, no, spot on from a Canister point of view. But whilst this is deploying, so when Nic was mentioning using VMware tools and other more traditional ways of being able to QS the workload, what we're doing from a Canister point of view, if we go into the actual blueprint that's deployed later on, it's actually using Elastic Dump, which is a native dump that basically takes the data from the Elasticsearch database and dumps it out to a tar file, which then gets pushed with that action set out to the profile that we're also talking. So hopefully that makes sense. Like PG dump for Postgres and other native, native tooling for data services are used.
Okay. Yeah, it makes sense, at least to me. So what we're going to do here, I'm just running a curl container because it's not because the Elasticsearch cluster pods are running that it's effectively working. So we need to query the Elasticsearch cluster. So it's going to take some time. It doesn't work necessarily out of the box. We're going to wait, I think, a couple of other minutes. In the meantime, if you want to see what's happening, so again, as I was mentioning, stateful sets are particular in the sense that every pod will be provisioned with a stable DNS name and ID. If pod 0 is master 0 is failing, is deleted, another master 0 will take over. That will be attached to the same PVC. Another thing about stateful sets is that so every node will keep the same PVC attached. The data will never be deleted. It's up to the user to delete the data or the PVC that is attached to the particular pod. And if you want to check the logs, you can do this as well. Let's say this one. We want to follow. And we will have some clues in terms of when the cluster will be formed. Yeah, and having a stable identity is very important, especially when you build a cluster on top, right? Because every member needs to have a stable identity, right? To stick to its particular role. Okay, so node ID. This may be good now. Let's check again. So let's run the curl container. And oops, no, this one. And okay, so now it's working. We have a response for our from our Elastic cluster. So we are ready to go to the next step, and which is so the second thing is, as always with Helm, you can choose to do different things. Like I've chosen to use curl to query via API, or you can use also Helm test for the chart that supports it, which works as well. So now a couple of things I want to see. So first, I want to double check that I've got all the PVCs that are using the Ondat storage class. So I can see that every every node is attached to the right, or every PVC is attached to that storage class. And then what I want to check is from on that perspective that I have all the volumes that are sitting in different, and the replicas are sitting in different availability zone as I've set them, right? So here, again, if I do get volumes, I have an ID, right? I mean the name here. I can do a storage OS describe volumes and then pick every one of them, and I will have more detail in terms of where the master is and all the different replicas are. So here I can see that my master is zone 1, first replica zone 2, second replica zone 3. That's good. Then I want to check for the second one. Here should be the same thing. I should be in the, should be sitting in the 3 different zone. And the last one, hopefully no surprise, should be exactly the same thing. Here you go. So 3 different zones. So we have a guarantee that in case of failure, you can, of AZ failure, all the nodes sitting in that particular AZ, the pods that are sitting on those nodes can be restarted on any other availability zone with the storage attached, which is not available by default in AWS, because if you're using EBS, for example, it's local to an availability zone. You can, create your own automation to promote them in another availability zone, but it's going to take time, probably 10-15 minutes. Here it's like it's more like second. So now we can install FluentD. So here, if you go to the editor tab, you can see all the manifests that are required by FluentD. So typically this is service account, roles, role bindings, and then the daemon sets. Nothing too surprising here. So I can just apply all those manifests in the cluster, and it's going to deploy FluentD for me. And then we monitor the creation of the daemon set. And we want to wait until we have 3. So it's coming up. 3 are there. So we have our FluentD running. And now the last step is really to install Kibana. So again, we're going to be using Helm for that one. So we add, we just verify that we have the Kibana chart available from the Elastic repo. And then just install it. The only thing, I think it's the value by default, but here we want to connect Kibana to Elasticsearch. So this is how you specify the address of the at least one of the nodes, right? So we're going to install it via Helm. So it's going to be deployed. And then we can monitor the creation of the pod. So it's a deployment. So in production, you may want to have more than one, but here is just one pod, a deployment with a single pod. And then, it needs to download first the image. And then what we're going to do is same thing again. We're going to check that Kibana is ready by just using curl and just querying the API. And hopefully we should have a response there. It's going to take some time to get there. Michael, do you want to add anything while it's loading?
Yeah, this bit takes a little bit of time, but I think EFK from a stack point of view is a super powerful, and one of the things that I like, so I've been familiar more so with the Efk Stack, which is using Logstash instead of FluentD, because FluentD is a daemon set that lives on each of the nodes within your cluster, but whereas Logstash, I don't know if you say like back in the day, is kind of the generic way of being able to just aggregate all of your logs into one place, use Elasticsearch to store those, and then have Kibana as your visual to that. Now, in the lab, for example, we're obviously deploying it, and we're using a lot of curl commands that Nic's running through. If you were deploying this in your Kubernetes cluster, you'd actually get a nice UI, a nice web front end that describes and displays all of this stuff. But I think this is a common stack that we're seeing out there from an observability point of view that is really quite common.
Oops. Okay, so this one, like before, is going to take some time, but in the interest of time, I will just go to the next. But I know for a fact that it's going to, at some point, converge. So I just like, okay, I can copy this. I'm going to check it in a couple of minutes anyway. So the last challenge is now to put some data in Elasticsearch, create, oh yeah, Kibana is not running, of course, needs to work first. So in the last challenge, what we're going to do is create some data inside Elasticsearch, then back it up, export it into Google Cloud Storage, and then we're going to remove that data and restore from Google Cloud Storage. Yeah. Yeah, this one take a couple of minutes. Yeah, still. In the meantime, is there any questions? No questions. Okay. What we want to see here is at some point we still have 502 answers, 302. We want to have 200. Once we have 200 answer, then Kibana will be up. Oh, here we go. So it should be.
Yeah, that looks good.
Where's the this one? Yeah, here we go. So all good, and the checks should work. Hopefully. Always misclick. Good. So last part. I know I'm a bit late, but we'll try to make it fast before the. So the next part will be the panel with our rockstar ladies. Okay, setting up the challenge. Okay, so the last part was going to take some time again because we're going to put some API query to Elasticsearch directly. Those one can take some time. So again, here we're going to play with Canister. So remember, we've installed the controller. Now this part we need to create all the custom resources that are required to back up Elasticsearch. So we're going to start with the profile, and the profile actually is where defining where you want to store the data. So here I'm going to explain what this command line is doing. So CanCTL is installed on the machine. So CanCTL will basically generate all the manifests for you. So here, for example, I'm using dry run in the end, which means that I'm going to see on the screen all the different manifests. And the other component, so -A, again, it's environment variable within the instruct sandbox, where I've got access to the local Google Cloud project ID. So the Kubernetes cluster K3s are running as VMs inside GCP, and inside that project, I've enabled the storage API, right? So I've got access to GCP, to the project ID, and I've got permissions to create storage, cloud storage bucket. So this is the environment variable for the project ID. Here, the service key, same thing. I've just parsed it from a variable. And then sandbox, I just have to generate a bucket name because it has to be unique, right, in the world. So here, this is the manifest that are generated. So you can see you have a secret to connect to GCP, and you have what is this one? The profile itself. So profile plus secret. The profile tells you that this is all the Google parameter, this is the name of the bucket, etc., etc. So now the only thing, if I'm happy with it, I'm just going to remove it from, I'm just going to remove the dry run option, and then it's going to generate the real resource within Kubernetes. Right? So here, the secret and the profile have both been created. And then here, I can check the profile content. So the object now is there. So the custom resource profile is effectively a first-class citizen in Kubernetes, and I've just created one instance of that particular, class, if that was a oriented programming object, right? Exactly that. So now that I've got the profile, I think good. Just checking I didn't skip anything. So Canister profile is there. I've done this. So now we want to create data within Elasticsearch. I'm going to log into one of the nodes participating into that particular cluster. And then I'm going to create an index. So remember, an index is the equivalent of a database. So it's going to take, again, about 2 minutes to get to the cluster. I'm not sure why it's taking so long. Maybe, I guess it's because it's a cluster. Every node needs to confirm it's happy with it. So Michael, any comments? Getting short of comments, like why people are waiting.
So, yeah, I don't know if I heard about
maybe the profile, like where do you?
Profiles.
Yeah, where can you put them? Like, so we mentioned Google. Like, what? How do you do on-prem?
Obviously GCP. Yeah, so it could be S3 compliant as well. So, like any on-premises object storage or any cloud-based that is S3 compliant, but including AWS S3 in itself, Microsoft Azure Blob Storage, and then there's also some efforts going into where else could you put them, i.e. like an NFS mount or some block-based storage as well. So if you wanted to send off those backups, like those tar files, those zip files to any location, then you can do that. So that's an option for any of those profiles. It's kind of the landing zone as to where we want to store those backups.
Okay, cool. So now what I've done here, I've created, as you can see, the index, which is the database, is called customer, and I've created a new entry. As I mentioned earlier, it's a semi-structured or let's say NoSQL database. Every document is based on JSON. So here we have name John Smith, and then this is the entry as represented in Elasticsearch. So now if I were to query, I think I should see that my data is here. So if I query Elasticsearch, customer search, so I see the entry with, it took like 648 milliseconds, I guess. It's just like the response from the server. So saying that, okay, we have an entry which is John Smith in the customer index, right? So we have confirmed, we have effectively data sitting now in Elasticsearch. So now we're going to back up Elasticsearch data. So we're going to create first the Canister blueprint. So as I said, blueprints are maintained by the community. So typically, I mean, you can create it yourself if it doesn't exist, but Canister has a set of curated blueprint you can find. I think on the GitHub repo, there's a lot of them. So in our case, we're going to be using the Elasticsearch blueprint. So again, the blueprint is a custom resource. And it is sitting within the Canister controller namespace. So I should see here that I've got one object, one instance of blueprints sitting in the Canister namespace. So this is good. In terms of the blueprint itself, if you want to take a look, it's there. So again, it's going to say, the command it's using to back up to the object store, right? So this is all the heavy lifting. You don't have to do yourself. So imagine if you're running stateful application in Kubernetes, you want to back up your data. How do you do it, right? You would have to create all this logic by yourself. Here it's just created as it's completely automated and it's managed by Canister. So a lot of, it's a lot easier there. Okay, now with CanCTL, we're going to create again the action sets, which we want to back up. So now the action set is backup now. So as soon as I hit enter there, it's going to start the process of backing up your Elasticsearch data. So again, it's pretty easy. It's just copy paste, and I want to monitor here the state, and then you can check the status of your action. So if I do this, so it's like it's currently executing phase backup to object store, so it's going to take approximately 1 minute. Any comment, Michael? Fill the blank.
Yeah, just before going on to the action sets, the way I've been describing these blueprints is more of an if this then that type workflow. If you think about I want to be able to move X, Y, Z data to ABC, then the blueprint enables that. It's like the logic, whereas the action set is the trigger to make that happen. Now, when we run this action set like this, we are literally just we're manually having to do this. Now, you could put that into a cron job. That doesn't sound particularly scalable in the Kubernetes world, the cloud native world. However, we are looking at how do we schedule this? How could we bring a scheduling component into this and leverage or make it a little bit more user-friendly as well?
Yeah, I agree. So here we can see that the status is complete, and just for the sake of it, I just want to check in my bucket if I have something new. So I'm using the Google Cloud CLI. It's just a container with all the right permission, because otherwise I cannot list the bucket. So if I just use gsutil ls-r and the name of my bucket, I see that now I've got a new backup a tar file or gzip file that is representing the data from Elasticsearch. So I've got effectively now a backup sitting in my bucket. So now the last step is to destroy and restore. So again, from one of the Elasticsearch node, we're going to delete some data. So we're going to delete the customer index, so the whole database, and just check that it's not there anymore after 1 minute. Oh, it's quite fast. So acknowledge. So normally, if I do grep customer in the list, I should see now nothing. So okay, empty return, which means that my database or my index has been deleted. So now again, I want to restore. How can I do that? Well, again, I'm going to leverage an action set. So I'm going to use CanCTL for this. So I want to restore from the backup that has been created before. So when I did the backup via the action set, it has created a new resource with a name, a backup name, right? And I'm just going to call back that object that point to my Google Cloud Storage to restore it, again, using CanCTL. So again, now it's going to return the status of that. So I'm going to check the status. Okay, it's still restoring. Maybe also take about 1 minute or so. So I'm just here monitoring the event section of the describe command from the action sets. So it's perpetually updated by the controller. Still restoring. And then the last part is basically to check again that the table is there. And then that will be the end.
Yeah, obviously making sure that obviously the data is now back.
Yeah, so status complete means that hopefully it's been restored. So let's check this. So let's connect again to one of the node and curl and grep for the index. And hopefully it should be back here. Yeah, it's there. So you can see now we have the customer index that has been restored. And I think, yeah, that was the last part. So let's check. What do I win if I have no mistakes? Yeah, so maybe I have a Ondat. Oh no, I already have a Ondat bag. I don't know. So yeah, I really enjoyed this lab because, yeah, I wrote it. So all right, so that concludes that part. So if you didn't do the lab and if you are interested, remember it will be available on demand. Just go there. If you want to, again, go through what I said, the session, it will be also put on YouTube after it's been recorded there. All right. So next part is the panel. So I guess we're going to take a couple of minutes break, and then we're going to come back. So enjoy some beer and pizza that are still there, and see you in a moment. Thank you.